Hi, physics. Mr. Janowski here. This is the second part of the chapter 34 slides. And briefly, in the first part, I mentioned the movie Idiocracy and electrolytes. Brondo's got them. It's what plants crave. Um, so, yeah, it's an important movie. Um, that's all I'll say about that. So, what units are named after this person? Well, this is Coulomb. What quantity are coulombs units of? Coulombs are units of charge. And what is the symbol of that quantity? It's Q for some reason. I guess the reason is we can't use C for everything. C is capacitance, so it can't be charge. Now, what units are named after this person? Well, this is volta, so it's volts. What units, I'm sorry, what quantity are they units of? Those are units of potential difference or just voltage. We can also say voltage is often easier. And what is the symbol of this quantity? It's V or delta V if you're emphasizing that it's a difference in potentials. You might say delta V. And this is the guy we learned last time. This is ampere. Amperes or amps are units of current, and the symbol of current is I. So I'm making a big push to make sure everyone is comfortable with the units and the symbols of things in this chapter for a couple of reasons. Um, Unlike physics 1, when we're often dealing with like a ball flying through the air and you can visualize that very easily, in physics 2, we're dealing with electromagnetism, so it's current going through wires. You can't visualize that quite as easily, and all the different quantities that are involved, they're kind of invisible. They're just harder to see. So it's very important that you have a very firm grasp of what things you're looking for. You've got to know what quantities are going on, because when you say electricity, do you mean electric potential energy? Do you mean electric field? Do you mean electric potential? Do you mean current? Do you mean charge? There's all kinds of different things. All of them are kind of difficult to visualize. So you've got to just be completely fluent in what are the quantities, what are their symbols. And of course, units are always important in physics as well. Now, what is conventional current? Conventional current is the rate of flow of positive charge. So I equals delta Q over delta T or dQ dt if you want to use the calculus. So current, we imagine, is positive charge flowing through a wire, through a circuit typically. But question 11, what actually flows through the wire? It's actually the electrons flowing in the other direction. So I've pointed this out before. This is completely Ben Franklin's fault, but don't be too mad at him. He took a guess. They didn't even know that there were protons and electrons when Ben Franklin decided to name one type of charge positive and one type negative. Um, yeah, he took a guess. It was a 50-50. Unfortunately, he got it wrong. So what is analogous to the narrow section of pipe that constricts the flow of water? Remember, we're using the water analogy very often in this chapter. This little narrow part, that's like a resistor. So here is an actual resistor, the kind you would use if you're playing around with circuits. On what's called a breadboard is the little typically green board that you plug the wires and the resistors and the batteries and things like that into. So that's an actual resistor, and this is the symbol for a resistor. And we'll be talking about resistors a lot today. And finally, a point about the language. I measured the voltage across the bulb. You don't measure voltage through things, you measure voltage across things. And you do measure current through things because voltage doesn't flow. You don't say you've got 120 volts flowing through your circuit. That's not what happens. Voltage doesn't flow. Voltage goes across things. Current flows. So current goes through things. So Ohm's law. So here's Georg Ohm. So Georg Ohm found that the current through a conductor or a resistor was proportional to the potential difference across it. So I current is proportional. Here's a proportionality symbol to the potential difference, V. So if I is proportional to V, well, therefore V must be proportional to I. And it turns out that V is equal to I times R. So the thing that relates their proportionality, something like that, is their resistance. So this is Ohm's law, V equals IR, or just Veer for short. So very important fundamental thing to know about electronics. Ohm's law, Veer. So Ohm's law relates voltage, V measured in volts, to current, I measured in amps, and resistance, R measured in ohms. So V equals IR. And when you put things in brackets, that often means these are the units of the things. So V, A, and the symbol for ohms is the capital Greek letter omega, which is basically my favorite. It's not basically, it is my favorite Greek letter, is capital omega. It's just really cool looking. So that's a capital Greek letter omega. What is a lowercase omega? We actually learned this last year. It looks like a W, basically. It's the symbol for angular velocity. That's lowercase omega. This is capital omega. So our symbol is resistance. Our quantity is resistance. Its symbol is R, and its unit is the ohm. And you write ohm has an omega like this. And is it a vector or a scalar? It's a scalar. It doesn't have a direction. So what are resistors? Well, resistors are resistors. If I hear the word resistor, I picture one of these guys first. So hopefully we'll be in person in some way this year, and we'll get to actually do the hands-on electronics lab. And when you're doing that and you're plugging things in, these are what resistors look like. Now there's this system of the different stripes. They're not just decorative. The stripes, if you know the color code, it's a way of figuring out what the resistance of that resistor is. There's a whole system for it. I don't remember it off the top of my head. You look it up when you need it. So yeah, when I hear resistor, this is what I think of first. One of these guys. But other things are resistors as well. The filament in a light bulb is a resistor. So if you've got an old-fashioned incandescent light bulb, the filament is a resistor. A cigarette lighter for a car. So cars always come with the little port for these things. They typically don't come with the cigarette lighter itself anymore because it's 2021. Who smokes? Um, but yeah, it's a resistor. So basically, the way this works is the voltage. One part of the voltage is applied in the middle. One part of the voltage is applied on the outside, and the current just goes around like this until it gets to the outside. And the current going through the resistor causes the resistor to heat up. You can also call this a thermo resistor. Although all resistors heat up to some degree, but some of them are kind of better and more predictable at it than others. Yeah, and that's what makes the thing hot, and that's what lights the end of the cigarette. So don't smoke, but if you do have an electric range, feel free to use that sometimes. Yeah, this is also a resistor. So you apply the current at one end. You apply positive voltage at one end. You apply the negative voltage at the other end, and that causes current to flow through this thing. And when the current flows through it, it heats up. That's how that works. And I don't know if you're familiar with the movie Caddyshack, comedy classic, great movie. But here's Bishop Pickering, one of the antagonists in Caddyshack. He gets struck by lightning. He deserved it. Don't feel too bad for him. But yeah, he's got current flowing through him, and he is resisting the flow of that current, making him a resistor. Now, are wires resistors? Well, yes and no. Wires are resistors. They do offer some resistance. However, the resistance of a wire is typically so low that you can just ignore it. So if you're analyzing a circuit like this, you're going to care about the voltage of this thing. You're going to care about the resistance of this thing, and you're going to pretend that the resistance of the other wires are just zero, because they're so close to zero. Now, they're not actually zero, unless we're dealing with a superconductor, but that comes later in the chapter. So yeah, they do offer some resistance, but it's usually so low compared to the actual resistors in your circuit that you just pretend like it's zero. So in bold, it says Ohm's law is true for objects that obey Ohm's law, which is the same thing as saying this thing is true when it's true. So there's not a whole lot of content in that statement, but that is basically how this works. Ohm's law is not like the law of conservation of momentum. Things break Ohm's law all the time. Nothing follows Ohm's law perfectly, really. So ideal conductors and resistors obey Ohm's law. If they were perfect, they would obey Ohm's law perfectly. Now, real conductors, so any actual physical wire that you have, and real resistors obey Ohm's law pretty well, as long as the voltage and the current and the temperature isn't too out of control. And then you have circuit elements like transistors and diodes that just don't obey Ohm's law. You can't use V equals IR to predict how much current is going to flow through these things. They just work differently. So here, look at this circuit. We have a 12-volt battery and a 3 ohm resistor connected as shown. What is the resulting current? Trick question. The resulting current is 0. And the reason the resulting current is 0 is that the switch is open. So yeah, always check your circuits. Make sure you've got a complete path. The switch is open. current can't flow through this thing at all. So this question, redux, same thing. This time we've closed the switch. What is the resulting current? Well, V equals IR, therefore I equals V over R. So plug in 12 volts divided by 3 ohms. 12 over 3 gives you 4. Volts over ohms gives you amps. So, yeah, that's how that works. So remember, we have a water analogy for resistance. Resistance is like a narrow section of the pipe that makes it harder for water to flow through. So if you had 2 pipes, which pipe would it be harder for the water to flow through? The narrow one or the wide one? It would be the narrow one. The narrow one is harder for water to flow through. Now, if you had 2 pipes and one was just a short, stubby one and one was a much longer one, which one would it be harder for the water to flow through? It would be harder for water to flow through the long one. That's less obvious than the top one, but the longer your pipe is, the more total resistance to the flow of water it's going to give. So remember these 2 ideas. Small area makes it hard. Let me say it the other way. Big cross-sectional area makes it easy for water to flow. Long length of pipe makes it hard for water to flow. Right. That's what I meant to say. So yeah, that's what this formula is basically. So here is your formula relating resistance, R, to resistivity. This is a Greek letter rho, to the length of your wire and to the cross-sectional area of the wire. I say wire, but it could be a resistor too. So the resistance of a wire resistor is inversely proportional to its cross-sectional area. That means when A gets big, when you've got a big wide pipe or a big wide resistor, the resistance goes down. It is directly proportional to its length L. So when the thing is long, like the long pipe here, your resistance goes up. And the thing that relates them is this quantity, rho, resistivity. So the symbol for resistivity is rho, the lowercase Greek letter rho. What are the units of resistivity? So this is a dimensional analysis thing. Basically, take this, solve it for rho. That's going to give you rho is equal to RA over L. And then again, the brackets indicate use the units. So if you plug in the units for these things, you get ohms times meters squared, because that's the unit of area, divided by meters. Well, one of these meters cancels, and you end up with units of resistivity of ohm meters. So that's ohms times meters. It's not ohms per meter. That would be a different thing. It's not being divided. It's ohm meters is what we got there. Not to be confused with what's called an ohm meter, which is a way to measure resistance. Not my fault. So anyhow, resistivity is a property of the material a circuit element is made from. The resistivity of your thing doesn't depend on its shape, doesn't depend on anything like that. It just depends on what the thing is made of. So materials are carefully chosen for their properties. Sometimes you want low resistivity, sometimes you want high resistivity. So you choose the thing. So here is a table of different materials and their related resistivities. It's saying rho naught at 20 degrees Celsius. Turns out these things are dependent on temperature. We'll get to that later. So if we look at the top 4 items, they have very low resistivities. So they let current flow easily. We've got a name for materials that allow charge to flow easily, that allows current to flow easily. And the name for those things is conductors. That's what a conductor is. So what do you notice about these materials? Silver, copper, aluminum, and iron? Yeah, those are all metals. Metals tend to be good conductors. Now in the middle of the chart, we have items that have much higher resistivities. So there's a range. It depends very much on the purity of the sample, and you purposely make them impure to whatever degree to get the resistivity you want. Don't worry about that for now. And yeah, times 10 to the minus fifth. So it's still a small number, but times 10 to the minus fifth is 1,000 times bigger than times 10 to the minus 8. So yeah, these still have much more resistance, much more resistivity than these guys. So yeah, we've got higher resistivities. So what are materials that allow charge to flow but not easily? Well, they're almost conductors. We call them semiconductors. So graphite, germanium, and most famously silicon these are semiconductors. And our last couple of things here, we've got glass and hard rubber. So very high resistivities. We went from 10 to the minus 8 to 10 to the minus 5th to 10 to the 12th to 10 to the 15th. So very high resistivities. These things don't let charge flow barely at all. And what are the names of these things? They're insulators. And another name for an insulator is a dielectric. But usually we say insulator. So key idea on this slide, resistance R is not the same as resistivity rho. Resistivity is the quantity. It has units of, it has a symbol of rho. It has units of ohm meters, and it's a scalar. So I know the words resistance and resistivity sound similar, but they're not the same thing. They're related by this formula, but they're not the same thing. So if we have a 9-volt potential difference and we're going to apply it across the length of this iron block as shown, what is the resistance? So the potential is going to be applied across the length. We're going to put plus 9 over here and 0 over here. That would be our 9-volt potential difference. So what is the resistance? You use your formula for resistance. First of all, I said it was iron, so look to your table, find rho, the resistivity of iron, plug that in here. The length, I gave it in centimeters. It's got to be in meters for this formula to work, so do your metric conversion. And the area, well, it's a rectangle, so length times width, and that's your area. And you end up with a resistance of, it's being blocked, but 2.43 times 10 to the minus 5th ohms. So a pretty small resistance, but that makes sense. This is iron. Iron is a conductor, so it's going to let charge flow fairly easily. Now, would the resistance be different if we apply the voltage top to bottom instead of across the length of the block? So instead of putting your positive terminal here and your negative one here, what if we put your positive terminal up here and your negative one on the bottom? Would the resistance be different? And the answer is yes, it would be different because you've got a different cross-sectional area if you do it that way, and you've got a different length. The length, if you're going top to bottom, is just 3 centimeters. Your area is 15 times 2 centimeters, converted to meters, of course. So, yeah, when you're talking about the resistance of a thing, you do need to know the physical dimensions of it, but you also need to know which way you're going to apply the voltage. Because if you apply the voltage differently through different sides, you get a different answer. So how would you calculate the resistance through a through a long round copper wire? Yeah, so typically we don't make wires that are square. We're much more likely to make them that are round. How would you figure out the resistance? Well, the length is easy enough to measure. The area, it's the area of a circle, which is pi r squared. So that's how you would do the thing. So to review, what units are named after this person? That's ohm. So the units are ohms. How do you write these units? You write it with an omega, a capital Greek letter omega. Yeah, so the guy's name was ohm, so omega was a natural symbol for his unit, for the units that were named after him. And what quantity are these units of? Ohms are units of resistance, whose symbol is R. What is Ohm's law? This is just burn this into your brain. VIR, V equals IR. And what formula relates resistance to resistivity and the physical dimensions of a wire? It's this one. R equals rho L over A. Resistance equals resistivity times the length divided by the cross-sectional area. That's it for part 2. Hopefully you found that helpful.